Welcome everybody to another problem-solving video. We'll start with a little bit of what I hope is review. First of all, here is a structure that has 3 carbons in it. It has 5 hydrogens and it has a positive charge. Please type in the name of this structure. What is it? What do we call it? It's something that hopefully looks familiar. This is the allyl cation. Recall that the allyl unit has 3 carbons in it, 1, 2, and 3. The next part of the question is, how is the positive charge distributed in the allyl cation? And you can answer that question with pictures only. No words are required. Well, whenever you have an allyl system of this sort, you can consider the delocalization of electrons from this double bond, from the pi bond, over here between carbons 1 and 2. And that generates a second resonance structure. You may find it helpful to keep the numbers on the structure. The double bond is now going to show up between 2 and 1. The hydrogens are all in the same places that they started. And the positive charge, where is it? If you don't have that in your structure, you can put it in now. The positive charge shows up on carbon 3. So if we enclose these 2 resonance structures in brackets, those 2 pictures give our answer in terms of where is the positive charge located in the allyl cation. It's not confined just to carbon 1. It should be equally shared between carbon 1 and carbon 3. Recall there's just one allyl cation and it's a hybrid of these 2 structures. Let's come over here and do a related problem. What about a system of this sort? We have the same number of carbons, same number of hydrogens, except now there's a lone pair on this carbon and a negative charge. What about the distribution of negative charge in this particular anion? This should be called the allyl anion. So again, using only pictures, tell us about the distribution of negative charge. Same idea, except in terms of generating the resonance structures. Let me put the carbon numbers on here. We're not going to start from the double bond and go over here because we would exceed the octet at carbon 1. Instead, you start from the lone pair. You come there. You can't stop because this would exceed the octet at carbon 2. And so let's put the lone pair onto carbon 3. So if you didn't get the structure, you can draw it now. You're going to have a second resonance structure. Again, carbons 1, 2, and 3. This second resonance structure shows a double bond between carbon 1 and carbon 2. The lone pair is now on carbon 3, giving it a negative charge. And the positions of the hydrogens are exactly the same. Of course, when you write resonance structures, recall none of the nuclei can move. What does this resonance picture imply about the relative bond lengths of C1 to C2 and C2 to C3? Which one is longer? And this may be a trick question. Well, neither of them is longer. They're exactly the same length because this resonance structure and this resonance structure are really the same by symmetry. They have to contribute equally to the real character of the molecule. And so the real molecule is going to be an equal contribution from each of these, which means that C2, C3 will be identical to C2, C1. We looked at the allyl cation. We looked at an allyl anion. There's one more member of this set of allyl somethings. An allyl cation has no electrons on one of the carbons in one of the resonance structures. So you would just have a positive charge here in the allocation. In the allyl you have 2 electrons here and a negative charge. How about the neutral compound, where you just have a dot there, an unpaired electron? What would you call that? Take a guess. How about allyl, and it's a radical. The word radical is typically used to refer to something where there's an unpaired electron somewhere in the structure. How do you expect this unpaired electron to be distributed within the allyl radical? So if this is carbon 1, 2, and 3 in the usual numbering scheme, is that dot, is that unpaired electron density confined to carbon 1? And maybe you've guessed it isn't. Can you show us where else it is shared? We have to do resonance structure writing again, but now because we have a single electron, we're just going to use a fishhook arrow of this kind. So what this means is take the dot from carbon 1 and use it to make, well, it can just make half of a new bond between 1 and 2. We need a second electron to complete that bond. So let's take the second electron from over here, from the double bond part of the C2-C3 connection. So we could do that. And then there's a second electron in C2-C3 in this double bond part. So let's take that and put it over there. So again, if you didn't get the arrow pushing part, can you use my arrow pushing to draw the resulting structure? We now have the same 3 carbon atoms, 1, 2, and 3, except there is now a double bond between 2 and 1. The hydrogens are all in the same places. And the dot is at carbon 3. Again, we have a situation analogous to what we had in the allyl cation and the allyl anion, where these 2 resonance contributors must contribute equally. So the dot is going to be equally shared between carbon 1 and carbon 3. The bonding is going to be intermediate between a single bond and a double bond for each of the bonds C1, C2, and C2, C3. Let's take this a little bit further. What if we have a benzene ring, like you've seen before in some of the video problem-solving exercises? You've got 5 hydrogens on the benzene ring, and then you have this carbon right here. What kind of site is this? What kind of group or position is this carbon right here? Type it into the little field there on your Zaption. This is the so-called benzylic position. And in this structure, let's put a dot there. So is that unpaired electron, is it confined to that benzylic carbon? And if not, show us where it's shared by drawing some structures. We can delocalize this unpaired electron in the same way that we did in the allyl radical. We would come here like that and make a new double bond between these 2 carbons, except we can only make half of the double bond with that 1 electron. So we're going to need another electron that we can take from this double bond, and then we can take the second electron of that double bond and put it on this carbon right here. If we draw the structure generated in that way, we now have a double bond on the outside of the ring. We have a dot there. All these other hydrogens are still with us. Is that the end of the story? Well, we can continue to move this dot around the ring. So we could go there, take an electron from this double bond, take the second electron and put it there. In which case the dot has moved over to this carbon. And we're still not finished because, again, you can recognize here this carbon, 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 3 carbons. This is really the allyl radical substructure. And so we can do one more resonance structure in this way and show that that unpaired electron is further shared around the ring of the benzene. So that is the complete set of resonance structures. We have 4 of them, 1, 2, 3, 4. The unpaired electron is shared from the benzylic site over here to this carbon, at this carbon as well, and at this carbon as well. So we might conclude, as far as radical compounds are concerned, this might be a pretty good radical in the sense that that radical is stabilized by delocalization over a number of carbons. Let's do a problem where we start out thinking in terms of resonance structures, but then we go a little bit deeper and consider what exactly the resonance structures are representing in terms of orbital overlaps. Here's a structure for us to consider. It's a carbocation, and then attached to that positively charged carbon are 2 hydrogens. And then the other thing that's on here is an NH2 group, and of course there would be a lone pair on that nitrogen. So what I would like you to do is imagine arguing this case in a court of law, but you might be hired as the lawyer for either side. So I'd like you to argue both in favor of this carbocation being a good carbocation. So why might this carbocation be stabilized as far as carbocations are concerned? And then on the other hand, if somebody paid you to argue the case that this carbocation should be destabilized, how would you do that? Well, let's start with the stabilized argument. The stabilized argument perhaps should have something to do with resonance, whereby is there some feature so that this carbon that is electron deficient could have some of that electron deficiency satisfied. Perhaps you came up with a resonance structure if I start from this lone pair and I share those electrons in toward the carbon. I would end up with a resonance structure that has a carbon-nitrogen double bond. Be on the lookout for charge conservation. If there's a positive charge in this resonance structure, there must be a positive charge over here. It's here on the nitrogen. That makes a good argument for some special stabilization of this carbocation, namely that a pair of electrons from nitrogen can be shared to satisfy the octet of this carbon. Of course, in this resonance structure right here, you don't have an octet on carbon, but over here you do. What about the counter argument? What if you had to try to convince somebody that this actually was not a good carbocation? What might you say? Well, if this is a resonance effect, there are 2 categories within the universe of electronic effects in organic chemistry. So if you were making an outline of all the different types of effects in organic chemistry, Roman numeral 1 would be electronic effects, And then big letter A under Roman numeral 1 would be resonance effects. But there's another one, big letter B under Roman numeral 1, and that is inductive effects. Inductive effects, remember, have to do with electronegativity. So does that help you? Can you think of an electronegativity argument that would say this is actually maybe not such a good carbocation? If nitrogen is more electronegative than carbon, then these electrons here in this single bond, you might argue, hey, these should be polarized from carbon toward nitrogen. And then what are you doing? Well, you are withdrawing electron density from a carbon that is already electron deficient. So if being electron deficient makes you pay an energy penalty, then sucking electron density away from a carbon that's already electron deficient, that's got to be a worse penalty, even more than that. So in effect, you have two things that are in opposition to each other. So in this particular case, they are opposing. They're not always going to be opposing, but sometimes they are, and here they are. And so, well, the judge has to decide between the two arguments. The judge is experiment or calculation, and it turns out that in this particular case, the resonance effect really wins, hands down, really. And this actually turns out to be a relatively good carbocation. Let me redraw the carbocation that we were just looking at in this way. What hybridization would you pick for this carbon right here? And remember, one way to think about hybridization is think about geometry and then think about the corresponding hybridization. And then the other way to do it is to think about hybridization first and then go to geometry. We've seen that those are really very interdependent. So type it in the Zaption, what hybridization for this carbon? This carbon has three things attached to it. So we would expect this carbon to be trigonal planar. And the hybridization that goes together with trigonal planar is sp2. The next question is, remember when we did sp2 hybridization, we mixed together the carbon 2s and 2 out of the 3 carbon 2p orbitals. There was one 2p orbital left over. What is it? And how is it oriented with respect to this picture? There's a leftover 2p orbital when you do sp2 hybridization. And that leftover 2p, recall, it is perpendicular to the trigonal plane. The way that I've drawn this molecule, the trigonal plane is the plane of the blackboard. So the leftover 2p orbital is oriented perpendicular to the board, like this piece of chalk. It's coming out of the board toward you with one of its two lobes, and the other lobe of the 2p orbital is receding straight back into the board. Artistically, that's difficult to draw. So can you redraw this structure just by rotating the molecule through 90 degrees and drawing it edge on? So try to make a picture with this structure rotated by 90 degrees, preserving the trigonal planar nature of this carbon. So this little symbol here is exactly equivalent to. I'm just going to rotate the molecular plane a little bit. I'll put a C here for this carbon. And so one of the hydrogens is going to be coming out toward me. The other one is going to be back here. The NH2 group is going to be there. And artistically, the benefit of this viewpoint is that that 2p orbital that used to be perpendicular to the board but coming straight out, when I rotate this through 90 degrees, now the 2p orbital is lined up in the plane of the board, and it's much easier for me to draw it in like that. And then, at least in this resonance structure, there's a positive charge associated with this carbon. At this point, please type into Zaption, what's in this leftover 2p orbital? Nothing. There's nothing in there. It's empty. Next part of the question. What hybridization do you pick for nitrogen? This is kind of a subtle question. So what hybridization would you pick for nitrogen? And then we're going to delve into why. There are two possible answers that one could reasonably give. One turns out to be better than the other. You might argue that this nitrogen should be sp3 hybridized because it has one thing, two things, three things, four things attached. So maybe the geometry of that nitrogen should be tetrahedral and it should be sp3 hybridized. But in point of fact, it's better to think of this nitrogen as being sp2 hybridized. So I'd like you to think about how could you draw this part of the molecule, sort of by analogy to the left-hand side of the molecule, sort of fleshing out the geometry of what's going on here with an sp2 hybridization at nitrogen, and how might that be helpful in terms of showing how this molecule could be stabilized? Let me just keep the left side of the molecule drawn in the same way. Trigonal planar carbon here, empty 2p orbital. Here is the nitrogen. And let's just stipulate that that nitrogen is sp2 hybridized. What would the consequence of that be? Well, just like for carbon, for nitrogen, if you sp2 hybridize, you're going to have a leftover 2p orbital. And why might that be a good thing? Well, if I put that leftover 2p orbital like that, what's in this leftover 2p orbital? So look at this structure. What's in this leftover 2p orbital? The lone pair. And remember, electrons have wave-like characteristics, so even though I've put the lone pair in this top lobe, that electron density is really spread out above and below the nitrogen, as indicated by the drawing of that 2p orbital. Where do I put the hydrogens? So nitrogen, we're taking it to be sp2 hybridized. Can you fill in the hydrogens on that drawing? These two hydrogens right here. Well, the nitrogen should also be trigonal planar, and one hydrogen will be here, and one hydrogen will be there. And then the final question is, why is this the best hybridization for nitrogen? What is it that having this 2p orbital with a lone pair in it allows me to do, electronically speaking? Well, you see how this 2p orbital, its axis, is lined up with the axis of this 2p orbital. And so now you have a full orbital perfectly lined up with an empty orbital. Just really quick, sketch a molecular orbital diagram convincing people that the interaction of this filled orbital with this empty orbital is an energetically favorable thing. I'll just come over to the side. Remember, our energy diagrams for orbitals look something like this. Here's the empty carbon 2p. Here is the filled nitrogen 2p. Running out of board here. Hang on. How many electrons are there in carbon 2p, at least according to this picture? There are none. How many over here? There are 2. When these 2 combine and mix together, we generate 2 new orbitals, one lower in energy, one higher in energy, and now look what happens. Both these electrons can be down here lower in energy. So it's always stabilizing to have a full orbital overlapping with an empty orbital. We should try to maximize that overlap. And the way to maximize it is to sp2 hybridize this nitrogen. Finally, last thing, can you redraw this structure? Let's turn it. We've got the molecular plane perpendicular to the board. What if I just take it and turn it back again by 90 degrees? Forget about the orbitals now. Can you just draw the positions of the nuclei with this structure turned 90 degrees? Another way of thinking about that is imagine that you were viewing this molecule from above. What would you see? So up here, here's my trigonal planar carbon. I can draw in, if I will, a double bond there. Nitrogen, hydrogen, hydrogen plus. So maybe surprisingly, it's better for this nitrogen to be sp2 hybridized than it is for it to be sp3 hybridized. Energetically, it's more favorable. You can get this really nice overlap. The molecule chooses this geometry, which implies that this nitrogen is sp2. Here's an interesting molecule. It's an alkene. It has a carbon-carbon double bond. And then it has 2 carbon-carbon triple bonds. Recall that things that contain carbon-carbon triple bonds are called alkynes. So this is an ene, and it's got 2 alkynes. So it's an ene diene. Ene dienes undergo a remarkable reaction. This is called the Bergman cyclisation. From the name of this reaction, it's going to make a ring. And then this is the name of the person who discovered this, Robert Bergman, who's currently a professor at the University of California, Berkeley. Here is the product of a Bergman cyclisation. There is a benzene ring type of structure. But as you may remember, benzene has the formula C6H6. But this starting compound, it's got 6 carbons, 1, 2, 3, 4, 5, 6, but it only has 4 hydrogens. So what's here is not a hydrogen, but a dot. And what's here is not a hydrogen, but a dot. If you're interested, put ene diene in the Googler, and you'll find a lot of very interesting information about naturally occurring compounds. Chemists sometimes call these natural products. They might be manufactured by a plant or by an animal, but they're naturally occurring ene dienes that turn out to be very powerful anti-cancer agents. So they kill cancer tumor cells very effectively. And the way they work is they're more complicated than this. They have great big rest of the molecule surrounding this ene diene unit. But they undergo this type of Bergman cyclisation. And as you might expect, these dots are pretty reactive. And they can abstract hydrogen atoms, for instance, from DNA. And so they really mess up the DNA of a cell. And remember, since cancer cells are replicating much faster than healthy cells, just by killing cells, sometimes you can get ahead of the cancer. But anyway, that's sort of a sidelight. Several questions about this. First of all, please tell me what is the hybridization of each of the carbons of this structure. This carbon right here, is attached to three things. It should be trigonal planar, so it's sp2. This carbon is linear, so it's attached to one thing and then a second thing. So the appropriate hybridization there is sp. This carbon is also sp hybridized. And then this molecule is the same bottom to top. So of course, this is sp2 hybridized. This is sp, and that is also sp. Next question. Write a mechanism, or write an aeroformalism, to show how this ene diene could be converted into this diradical. Trace the electron flow using the appropriate type of curved arrow. I recommend numbering the carbons. 1, 2, 3, 4, 5, and 6. And then over here, we kind of have to guess where are those carbons. Maybe I'll guess 3, 4, 5, 6, 1, and 2. So what do I need to do? I need to make a bond between carbon 1 and carbon 6. You see there's no bond here, but there is a bond over here. And then I need to reduce the bond order between 1 and 2 from triple to double, and same with between 6 and 5. So how might I do this? I have a sense, since my product has unshared electrons in it, that perhaps I should be pushing the fishhook type of arrows. So what if I start here from the triple bond? I take one electron from there to make half of a bond between carbon 1 and carbon 6. And then I'll take one electron from here to make the other half of that bond. And then where does the second electron go? Well, the second electron I can just put on carbon 2. And the second electron from here I can just put on carbon 5. So actually, those arrows, that does it, right? That takes me from the ene diene to the Bergman cyclized product. You might wonder, it looks like carbon 1 and carbon 6 are kind of far apart from each other. So actually, these cyclizations require some heating to get the molecule to flex a little bit, where carbon 1 and carbon 6 can get close to each other. In the ene diene natural products that I told you about, there's often some triggering event where some other part of the molecule is altered, and that helps to bring carbon 1 and carbon 6 close enough together so that this cyclization can take place. So sometimes these compounds, these ene dienes, make great drugs because you can deliver the drug, and then there's something that happens in the cell that changes the molecule in such a way that the ends of the ene diene come close together. The Bergman cyclization takes place. You generate this diradical, and this diradical reacts with the DNA of the cancer cell, and eventually you can kill some of the cancer cells. Last part of this question. What hybridization do you pick for carbon 2 and carbon 5? Carbon 5 and carbon 2, each is attached to three things, if you will. One carbon, another carbon, and a dot. Moreover, carbon 5 seems to be engaging in a double bond here. So the proper hybridization for carbon 5 is sp2. And I guess I lied. That wasn't the very last question. The very last question is the following. What type of orbital is this lone electron in? Either on carbon 5 or on carbon 2. What type of orbital is that? Well, if carbon 2 is sp2 hybridized, it's using one of its sp2 hybrid orbitals to make a bond to carbon 3. It's using a second of its sp2 hybrid orbitals to make a bond to carbon 1. And then it's using its leftover 2p orbital to make a double bond to carbon 1. And so what's left? This orbital right here, that's the third sp2 hybrid orbital on carbon 2. So this electron is in an sp2 hybrid orbital, as is this one. This is an sp2 hybrid orbital on carbon